All right. Buongiorno tutti. Welcome back, Physics 2. We're going to be continuing on with chapter 21 in part 1 of Wednesday's lecture for week 13. And so I left you on a bit of a cliffhanger on Monday's lecture that we would need to be talking about something called electric flux. So in basic terms, electric flux is the electric field passing through a given area. So what we're going to be doing is we're going to be building through the different properties of electric flux, which is going to lead us into Gauss's law. So let's go through the properties of electric flux. And this can be very useful because Gauss's law, what we'll see, is leading to a surface integral. So if you are feeling overwhelmed by looking at it, go back to this section and recognize that you've got all the tools you need to break down these different properties. Okay. So, property 1. The direction of electric field. So it would make sense that the direction of the electric field would impact the flux. That's basically how we started the chapter. So we saw this already in our study of boxes, or our what's in the box game. More fun to play when there's more of you around. All right, so couple of things. So you know that something has charge and is positive when you've got a field in it that points out. So this would be a box with a positive charge enclosed. And then this would be a box. So we've got fields pointing in. This is a box with a negative charge enclosed. So both of these boxes have something in common in that they do have a charge inside. And the field lines are telling us whether it's a positive charge or a negative charge. All right, so it is also possible to have a box in which the net charge inside is 0. So for example, if you've got a box where the charge is parallel to the surface. So a box with 0 charge. So it is parallel to the surface. It's running right through it. So it's not pointing towards something that must be inside. There's something else outside of this area that is emanating that field, and it has nothing to do with this box that we have drawn. So parallel to the surface, running right through. So maybe there's a positive plate here emanating these field lines, but it's not inside the box. So for this particular box, the total flux is 0. All right, so we know flux can be positive, negative, or 0. So let's flesh the sign out in a little bit more detail. So the sign of flux. All right, so the sign can range from -1 to +1, and it can also be 0. Oh, something else ranges from -1 to +1. Oh, wonder if it's going to come into play later. I don't know. So the extremes, of course it's going to come into play later, would be -1, 0, and +1. All right, so now let's look at how we deal with the in-betweens. So what about the in-betweens? Okay, so let's look at electric field with a couple of different angles. So here we've got, this would be +1. This would be a little so we're just moving from plus to minus, where this is parallel, so this is 0. So this is a little less positive to 0 to a little less negative to a fully -1. And so what we can see here is that electric fields have different angles. And what this is building towards is giving us the relationship between the angle of the field and the flux. So we're looking at the relationship between field angle and the flux. All right, so we should introduce something that could encompass that term. So let me introduce to you n hat. This is a unit vector perpendicular let's try that again, to the surface. So here is our surface, and here is n hat, and then our field might be here. So we can look at the angle of the electric field with relationship to what is essentially the normal vector on the surface. And from there, we could get an angle. So let's look at the cosine of this angle. Oh my goodness, doesn't cosine run from -1 to 1? Why, I think it does. All right, so if the electric field and n hat are in the same direction, theta equals 0 degrees, and then cosine theta is +1. And then if the electric field is perpendicular, also sometimes written like that, to n hat, then theta is equal to 90 degrees, and cosine theta is equal to 0. So this would be parallel to the surface. And then if the electric field is 180 degrees from n hat, then theta is 180 degrees, and cosine theta is equal to -1, which is exactly what we've just built out. All right, so now we can see the relationship between electric field and the angle of the electric field. Okay, so let's move on to the next property that would reasonably make sense to be related to flux. The magnitude of the electric field. Not all electric fields are the same. You know this, some are big and some are small. And God loves them all the same. Oh, I've read too many books to 4-year-olds. So let's say you had charge Q inside this box. So you would expect you would get field lines that would be proportional to charge Q that would be inside that box. Now let's say you put twice charge Q inside of a different box, you would expect that those field lines would be twice the size. Bigger charge, bigger field. All right, so to get double the field, you need double the charge. Therefore, electric flux is proportional to the magnitude of the electric field and cosine theta of the angle between them. All right, so let's put these two things together and see where we land. Oops. Technical difficulties, just a moment. Okay. So E cosine theta can be written as E dot n hat, which is equal to E times the magnitude n hat cosine theta. And the magnitude of a unit vector is 1. So recall, and that would be true for any unit vector. Okay, so what you should recognize here is we have a dot product. And let's make sure that the dot product is giving us those extreme results that we would expect, that +1, -1, and 0. So for the outward field, so E dot n hat is equal to plus E 0, 0, dotted with 1, 0, 0 is equal to plus E. So this, of course, would be for the field that is perfectly perpendicular to the surface inward. E dot with n hat would be equal to minus E 0, 0, dotted with 1 minus, or 0, 0, no minus, is equal to minus E. Once again, this is the 180 degrees setup. And then the parallel field. So this is where the electric field and this normal vector, which is perpendicular, are perpendicular to each other. So E dotted with n hat. So we would have 0 for the x component, E and y, and 0. And as they're perpendicular, we could have a value here in x, 1, 0, 0, and this is, of course, equal to 0. So far so good. Everything's working out exactly the way that we would expect it to. Now, there's another property we need to talk about, and that is the surface area. Flux has to do with a particular area that you are choosing to look at the field lines to infer the charge that is inside. So, for example, you have charge Q, and we'll have charge Q over here. These charges are both, let's make them positive. And so you're going to radiate out the same size of field lines. Now, if you enclose this Q in a tiny little box, you're going to see some substantial field lines. Now we're going to do the same size field lines on this Q, only you're going to enclose it in a much bigger box. So the field lines are the same. However, because the surface area that you have chosen to look at to analyze these two things are different, we can see that what you would measure in terms of field strength would be different. And this makes sense with our understanding of the relationship between charge and the strength of the strength of electric fields, is that it is strongly distance dependent. So you're measuring the field at a larger distance here than you are here. So surface area, surface at further distance from Q, surface at closer distance to Q. All right, so what we can see here is that your choice of surface area is going to impact your calculations for electric flux. And yes, you get to make a choice of your surface area. Calculations for flux. All right, so we can put all of this together. And we get, finally, our calculation for electric flux. So flux, the symbol for flux is this. Well, the symbol for electric flux, capital Phi sub E, is equal to A E times n hat cosine theta. Now, make sure you include the subscript E here, because we will also be learning about magnetic flux, which of course will have a different subscript. So make sure you get into that habit now. All right, so we can also write flux in terms of the vector A, which represents the area of the surface. So flux in terms of the A vector. A vector is the area of the surface. So in that case, electric flux is equal to E dot A. All right, so let's do an example. So we're going to calculate the electric flux through a rectangle. That is 10 centimeters by 20 centimeters. The electric field is 200 newtons per coulomb, and theta is equal to 30 degrees. So our electric flux is equal to E dot A, and in this case we've been clearly set up to use the cosine expression, so the EA times cosine theta, electric flux is equal to 200 newtons per coulomb times our area, which is 0.1 meters times 0.2 meters times cosine of 30 degrees. And so we get our electric flux is equal to 3.5 newtons per meter, or Newton times meter squared over coulomb. So flux is in units of newtons per coulomb times meters squared. So field per unit area, or field times unit area. All right, so pretty straightforward so far. Let's do another definition and a few more conventions. All right, so just this is also an aside. So electric flux E is equal to the sum of the surface E dot n hat times delta A. So basically you're summing up all of those field lines over your surface that you've enclosed. So I want to introduce a concept of A perpendicular. So let's say you've got your area here and you've got your field coming out in that direction. So you could have A perpendicular, which is right here. So you've got your surface area A, you've got your field E, you have n hat right here, and A perpendicular is the perpendicular projection of the area. It is perpendicular to the electric field. All right, so we'll end this aside. All about A perpendicular. And let's go back to this sum expression for flux. So electric flux is equal to the sum from I equals 1 to n EI dot delta A I. So basically you're just summing up all of these field lines over this area. And then if we take the limit as delta A I goes to 0, then we have flux is equal to the integral E dot dA, which is, of course, our sum. And this is Gauss's law. And yes, I expect both classes, algebra and calculus, to know this expression and to write it in this way. But don't worry, we will not be doing any integrals that you can't handle. Mostly we're going to be looking at dA and thinking about different surface areas. And surface areas are something that everybody in this class can calculate. Okay, but it is important to keep things in their proper notation. So we're going to be keeping this notation in both the classes. All right, let's move on. So, what Gauss's law is describing, ooh, that's really crooked. There we go. All right, so Gauss's law is the total flux summed over a closed surface. And it's typically written is equal to the surface integral. So this is the notation for a surface integral, E dot dA. So this is really the notation I want to see. And so this indicates summing over every point in a closed surface. So, and that's a concept everybody can understand. Basically, we're just looking at a surface and we're just looking at every single field line coming off of it and we're adding it up. And we're going to be looking at conditions that are pretty straightforward to calculate. Don't worry about that. All right, so building on this, the precise relationship between charge inside the surface and flux is E dot dA is equal to Q enclosed over epsilon naught. So this is charge inside, and this is the permittivity of free space, that fundamental constant we've been seeing all semester long. So electric field over the surface, and then of course the area, the surface area. Okay, so continuing to flesh out Gauss's law, note, it does not matter how the charge is arranged inside. Only that it is contained in the surface. In fact, we may not be able to, depending on the arrangement, we may not be able to know very much about it. All right, and then further note, a charge outside may impact the position of the lines from the surface, but not the net amount. And I'll show you what I mean. So let's say we have a dipole. So we have a positive charge here, and we have a negative charge here. And we're going to enclose each one of these inside of some Gaussian surface. Doesn't matter. All right, so let's think about these field lines. So let's do different colors. We would have field lines which would be warped by the negative charge here, so in this case you've got the field lines coming in here and the field lines which would want to go out in all directions from here. And we can see these field lines here. These have been altered by the presence of the other charge. But the count stays the same. So in both of these cases, positive Q and negative Q, the magnitudes are the same. We can see 6 field lines coming out of each. That's still true. It's just that these have moved towards the other charge. So this is area 1, area 2. All right, so let me write a couple notes just kind of quantifying that. I want to make sure you have this down. So we can see A1 has positive Q A2 has negative Q. Positive Q impacts negative Q, but charge enclosed is the same. And what we care about is charge enclosed. So Gauss's law is only about charge enclosed. It doesn't care what is going on the outside. All right, so there's a cool little thing we can do. We can relate Gauss's law to Coulomb's law. All right, so let's look at a point charge. We know, we did point charges all the way back in chapter 13. Do you remember those days when you got to sit in a classroom? It was great. So here we go. Here's our point charge enclosed. So, and we know how to calculate E for a point charge. So let's say we enclose, which we've already done, our point charge with a sphere of radius r with charge at the center. And the reason we've chosen a sphere is spheres are really easy to calculate. So we've chosen a symmetric shape. Easy to calculate. All right, so if we enclose a point charge within a sphere, we know E has the same magnitude everywhere on the surface. And we know it is going to be parallel to dA. It's also going to be perpendicular to the surface on every location. All right, so we can then write the integral of Gauss's law. So we have our point charge. It's enclosed in a sphere. So we have E dot dA, EdA. This is equal to, E is constant for all area. So we can pull that out in front, EdA, which is equal to, if we look at the surface integral of a sphere, we're just going to get back surface area of a sphere. So this is equal to E times 4 pi r squared, surface area of a sphere. All right, and E is the same everywhere. Due to symmetry. Okay, so then it follows Q over epsilon naught is equal to the surface integral E dot dA, which we've already calculated to be E is equal to 4 pi r squared. And this works because E and dA are perpendicular to the surface at each point, so cosine theta is 0 because E and dA are perpendicular to the surface at each point. All right, we solve for E. So we have Q over epsilon naught is equal to E times 4 pi over R squared. And we get E is equal to Q over 4 pi epsilon naught R squared. How cool is that? Coulomb's law. And you can also derive the reverse. You can derive Gauss's law from Coulomb's law. All right, so I will end part 1 of Wednesday's lecture here on that really awesome note, and I'll see you for part 2.